Good morning. So, it is now time for us that we go forward with our double slit diffraction and finish it up actually. We had started yesterday and today it is our second part of the double slit diffraction, and we will know about the rest of the points which we are supposed to know all about double slit diffraction, particularly to say Fraunhofer diffraction. Okay. So before we start today's discussion, let us just take a recap of what we have already done yesterday. We have seen first and foremost how the figure looks like for a double slit diffraction setup. Fine. Then we have calculated the path difference between the two sources, where these two sources were situated individually. The first one on the slit number 1 and the second one was considered to be consisting or situated at the slit number 2. Fine. So we calculated the path difference between these two sources. From path difference, we moved on to finding out the phase difference between these two sources. Once phase difference was calculated, then ultimately we used the concept of vector addition with a finite phase difference between them, and then we calculated the amplitude, the resultant amplitude caused by these two waves. Fine. And from there ultimately we decided, or we found out the intensity which would be seen on the screen due to a double slit. Right. So these are the 4 things which we have already discussed and calculated in our last class. So let me write down the last result which we had received yesterday, which was the intensity due to a double slit diffraction pattern on the screen can be written as 4n square a square sine square alpha by alpha square cos square beta. Fine. Now, as I always tell you that whenever we are writing this kind of an equation, it will always be needed for us to write down the individual values of alpha and beta. So, what was alpha for us? Remember, alpha was pi by lambda a sine theta, and beta was found to be seen as pi by lambda a plus b sine theta. So, beginning to think about what is this theta? Theta is the angle by which the wave or the light ray has diffracted, has bent. Alright, and then this dimension A is the slit width, whereas this B is the distance between the two slits. This is what we had discussed, right? So, with these information in our hand, now we are ready to move forward to our second part of double slit diffraction. Alright. So now what are the points which are still to be discussed? Reminding all of you, when we have got till these results, the next points or the next steps that we are supposed to do would be to find out what will be the conditions for getting the central maxima, the condition for getting secondary maxima, and also the condition for getting the minima. Right. So these are the 3 next points or steps that we are going to do in today's class. However, students, please remember that when we are going to find out the conditions for maxima or minima in the double slit case, it is little different from what we had done in case of single slit. And why am I saying so? Please remember that here the contribution is not only coming from diffraction from a slit, but we also have a contribution from the interference between these two. So when these two are going to give us a resultant, even there we have seen that both the phenomena are going to have their contribution. So now in the same manner, thinking in the same line, when we are going to find these conditions or we are going to state the conditions, we will have to bring in the conditions for an interference maxima or minima. Similarly, diffraction maxima or minima. And their effects will actually be a combination. The final result will be a combination from both of these. So now let us begin our discussion, or rather the calculation. Now, what I have to actually tell you all, that in this scenario, the first step or the easiest step would be to talk about the condition for principal maxima. All right, or the central maximum. It is generally we call it a central maxima. Sometimes you will find that we call it as principal maxima as well. Now, if you remember the particular figure, or also the consideration that we have been doing till now, the discussions that we have been doing till now, where do I get, or in which condition do I get the central spot, the maximum intense spot? Where, if you remember, say, starting from this very expression, when will I get the maximum intensity? I will get the maximum intensity when this sine square alpha by alpha square will also be 1, as well as cos square beta will also be 1. So, in order to get both these conditions, both these terms to be 1, what is the only possibility? The only possibility is that sine alpha by alpha must be 1 and cos beta must be 1. If I ask you which condition or for which angle are we supposed to get this, you all will readily say that we can only achieve this when in this case alpha is equal to 0 as well beta is equal to 0. Isn't it? For the individual values of alpha and beta assuming the value 0, that means where the bending of light has not occurred at all, we are going to get the central maximum. And see, when I take this alpha is equal to 0, what am I going to get? We had already discussed this in our single slit as well. So if alpha takes the value of 0, since pi, lambda or individually a is not 0, sine theta must be 0. Sine theta must be 0. Similarly, if beta individually is 0, once again in this scenario, sine theta is 0. And as I was telling just little ago, what is the meaning of sine theta is equal to 0? This theta is equal to 0 means that the bending of light has not occurred. It has only passed through the slit in a straight line, isn't it? So, the situation or the condition for getting central maxima for double slit as well is the same condition as single slit, which is when the light rays have not deviated or deflected at all. They have just moved in a straight line path. And if you remember our figure that we draw, the point P0 where they were converging, that is our central maxima, right? So the condition for getting the central maxima in the double slit as well is the same condition wherein there is no diffraction as such, there is no bending of light, giving us alpha is equal to 0, beta is equal to 0 and eventually giving us that sine theta or theta itself is equal to 0. Alright. So this was our condition. So if I write it down as a precise condition, so my condition for central maxima can be written as theta is equal to 0. No bending. This is very easy for us to realize as well. Fine. Now let us move forward to the next discussion, which is getting the conditions for maxima and minima. Now, as I was telling you in the beginning, that in this case, when we are discussing about the double slit, we will have to individually think about the maxima and minima conditions for the diffraction occurring, as well as we will have to also think about the maximum or minimum conditions occurring because of the interference term. Yes, Arjun, you are right. Alpha tending to 0, or actually it is very small alpha, or alpha is equal to 0. Right. So, in this case, as I was telling you all, we will now have to discuss individually the maxima and minima conditions for the diffraction, as well as maxima and minimum conditions for interference. All right. So, now let us move forward. Now, see, what are we going to discuss over here? Let me just rub this away. No requirement of this again. So now let me just remind all of you about when do we get the maxima or minima in case of the diffraction occurring. All right, reminding all of you, please see that when we are doing this result also, the result from the single slit diffraction is being used time and again. So whenever you are preparing for double slit as well, it is always advised that you should be very, very mindful about all the results that you have learned from the single slit. Okay, so in this scenario, let me just write the condition for, say, maxima in case of diffraction. We are considering the diffraction maxima. Now, can I now ask you to remember and tell me what were the conditions for getting the diffraction maxima, specifically the secondary maxima? We were conditioned for secondary maxima. Obviously, I should not be missing this point of secondary maxima. In case of diffraction, how did we receive that? Remember what we had done in order to calculate the maximum in this case for secondary maxima, we had differentiated the intensity expression with respect to alpha. We had done di d alpha and then we had equated it to 0, and we had finally received an equation something like this: alpha is equal to tan alpha. And when we had solved this, remember we solved this with the help of a graphical method, right? So we had plotted a graph with y is equal to alpha. We had plotted a graph with y is equal to tan alpha. Those who are not able to understand it, please go back to the single slit class, that video, and do watch it. All right. So we had individually plotted these two graphs, and the points of intersection were our values or the solution for this alpha value. And reminding all of you, we had received the conditions for secondary maxima at the values something like, if you remember, plus minus 3 pi by 2, or we had also found out something called plus minus 5 pi by 2, 7 pi by 2, and so on. These were the points where the y is equal to alpha graph and y is equal to tan alpha graph were intersecting with each other. And we had received the result that this particular condition 3 pi by 2 is going to give us which maxima? The first order secondary maxima. For 5 pi by 2, we had received the second order secondary maxima, and like this. And this plus minus was telling us that we are going to receive two individual such results, two maximas in both the sides of the central maxima. Correct? So this is what we have already done. Now, if I want to summarize this and if I want to write it like a general formula, what will I write? That I am going to get the secondary maxima of diffraction for all values of plus minus twice n plus 1 pi by 2. I hope all of you are able to relate with this particular general formula. So this is the condition for secondary maxima received on the screen caused due to diffraction. Now in this particular class, we are talking about diffraction from the slit S1 as well as the slit S2. So this is what is going to be, the same condition is going to be followed in case of slit S1 and slit S2. And remember over here that what was the condition for the minima that we had received? For the minima condition, remember, for minima in case of diffraction, what was the scenario? We had to consider that sine alpha, if I have to write it actually, if I write it, condition for minima, the condition for minima we had received as sine alpha is equal to 0, and we had considered for what values of alpha that I will be getting this 0, for some value of sine plus minus n pi. However, reminding once again that what are the allowed values of n over here? N must be 1, 2, 3 and so on. We will not be considering the n is equal to 0 case because that will actually give us our central maximum. Fine. So these were the two conditions for secondary maxima and the minima condition for the diffraction occurring. And we had plotted the intensity distribution something like this. Something like this. Correct? So if you are, when you are going to draw this kind of a figure, maybe in your examination, what are the things that you have to remember? If you are plotting, say, alpha in this case, along the x-axis, if you are plotting alpha, what are the values? What are the values of that alpha when I am going to plot the maximas at? These maxima values are all at odd multiples of pi by 2. Whereas for minima, I am going to get all the even multiples of pi. Right? So, with these things in our mind, we can easily draw the figure for diffraction maxima and minima. But now we have to move forward and also think about the contribution from interference as well. Right? So, if now within this double slit result, I have to incorporate the results or the contribution from interference as well, now I will have to look into the conditions of getting maxima or minima for our cos term, isn't it? So, if I could keep it over here like this, or maybe we will have to write once again. So, if I now go back, let me keep this figure. Let me keep this figure. This is for our diffraction. But now what are we doing? We are finding out the condition for interference, say maxima. Now, which term is giving me the contribution due to interference? It is my cos square beta. This is the term which is giving us the contribution from the interference occurring. In this scenario, if I ask you when will this cos square beta be maximum, what will be your answer? Obviously, you will agree with me that when cos beta is equal to 1, isn't it? So, when cos beta is equal to 1, the contribution from the interference is going to take its maximum value. And what are the values of beta for which I can get the value 1? Remember, what will that be? May I not write that this beta, the maximum over here, is received for all values of plus minus n pi. Now, students, please remember that we have used this integer value n for the diffraction. So, I am deliberately not using this n once again. I am using some other number, say m, so that it is easy for us to remember that the values of n are for diffraction and m are for interference. Okay. So, when this beta takes up any value between plus minus m pi, I am going to get what? I am going to get the condition for interference maximum. Right? If you put the value of beta, or beta is equal to plus minus n pi, and who was beta? Beta was pi by lambda a plus b sine theta, which is now equal to plus minus n pi. So, can I not write from here that ab sine theta is something like plus minus n lambda? However, reminding once again, this integral value plus minus m lambda is now the condition for maxima in case of interference, right? And remember when we had written down cos or a sine theta, I have forgotten to write theta here. Remember what we had done, what was the condition we received for the minima of diffraction? We had received the minima of diffraction at a plus minus n lambda. So this is where both of them are so different, so starkly different, right? So this is the condition for my interference maxima. On the other hand, now if I have to calculate what are the conditions for interference minima, now all of you will agree with me that this cos term has to go to 0. And in this scenario, going back to the same kind of discussion or calculation, you all will agree with me that this can only occur for now 2n plus 1 pi by 2 values, or a plus b sine theta is something like plus minus twice n plus 1 lambda by 2. I have jumped one step, but I guess all of you will be able to understand what I have done. So see, in this scenario, this path difference being odd multiples of lambda by 2 is yielding us the conditions for interference minima. Alright, now including these two, the conditions for minima and the conditions for maxima, if I wanted to draw the pattern or the intensity distribution, how would I draw it? How would I draw it? I would draw the interference intensity distribution something like this. Where the amplitudes of all these maximas are same. And reminding all of you once again, when you are going to draw this, what are the angular values that you are going to remember? That in this case, we are going to get the maximas just opposite to the values of diffraction maximas. Opposite in the sense, if diffraction is giving me the maxima at odd values, in this case, I'm going to get the maximas at the values like say n is equal to pi, 2 pi, 3 pi, and so on. On the other hand, I'm going to get the minima at 3 pi by 2, 5 pi by 2, and so on. Just the places where maxima would be received for interference, I would be getting the minima for diffraction. And now, considering these two occurring simultaneously, what are we going to see on the screen? The one which we have to see on the screen will be an effect of the combination of both of these. And you know how basically that thing appears? That thing appears in a very, very interesting manner. Let me just take some time and try to show you what is the pattern that we see or the intensity distribution that we see. In this scenario, suppose this dotted line is the one which has been caused by a diffraction pattern. And reminding all of you that interference, if I was drawing, I would be drawing in all the amplitudes to be same, all the distance between the maximas to be same, and so on. When we superpose these two, when we consider or this contribution together, we receive the intensity distribution something like this on the screen. Isn't this very, very interesting? So as if, what is the meaning? When I'm drawing this, what am I trying to show you? I'm trying to show you that in between, say in case of diffraction, suppose there was a spot like this. Say when I was considering say this is my screen and my slit was say like that of a straight line shape, then what would be my shape or my screen showing me? In case of single slit, I would be seeing like a very bright maxima in the center. This entire thing would be bright. There would be a minima condition, maybe say in between these two, a dark situation on both sides. Then again, we would be seeing another say bright spot, but this time the brightness would be less and also the thickness also would be less. Like this kind of a thing we would be seeing in case of the screen for a single slit. But the moment now we have increased the slit number from 1 to 2, what are we going to get? Do you know? Within this area also, I am going to get many such alternate dark and bright fringes. And this alternate dark and bright fringes is the cause or the reason behind it is the interference term. All right. Similarly, in this case also, in between here also, I would be getting a few more interference maxima and minima. And when I have plotted this, say these are the angular values and this is the intensity, I can plot it in this manner. So this is what happens when we do the experiment with double slits. All right. Now Shrestha has asked me, Acha, I have two very good questions. Shubhronil has asked that for interference intensity, okay. How the interference in case of the intensity is same, you are not able to understand. See, since we have not discussed about interference in entirety in our class over here, this condition has not been discussed in general. But see what happens in interference. Shubhronil, please note this little carefully. What happens in interference is, say I have started with an intensity I. In some places you will see that there is complete darkness, and in some places you will see that there are bright fringes. However, when we add up these intensities, it is seen that it is exactly equal to the intensity that I had started with. And in this scenario, this distribution of intensities is equal for the first order maxima till the nth order maxima. The distribution remains the same. However, not only for the bright points, the dark points are also having the equal intensity, which means darkness everywhere, which is intense. This distribution is again same. And also the fringe width also remains the same, which means the distance between two maximas and distance between two minimas is called fringe width, and that is also remaining same for individual all the orders. However, this is not so when we are coming down to diffraction. All right, remember when we are doing it with the help of sine square alpha by alpha, these values, see what we have not discussed here because it was not required for our discussion. We have not actually seen that what is the distance between each of the say maxima, distance between the two maxima, distance between the two minima. But I can always show you like that. Say what we had received. Remember we had received sine theta, a sine theta is equal to say n pi. So can I not write sine theta is equal to m pi by a? And since in this scenario, sine value, the theta value is very small. Whenever diffraction is occurring, since theta value is very small, I can always consider sine theta to be like this. So theta value is like this plus minus. So if I take the value of m is equal to 1, I am going to get my first position. So that will be received at plus minus pi a. But now if I ask you what will be the position of theta 2, that will be 2 pi by a. So from here, when I want to know what is the angular distance between the second order and first order, you will see that it is coming out to be exactly pi by a. The same thing will remain for the rest of them as well. So like this, it can be shown that the angular distance in case of interference remains the same. Okay. However, now getting back to the second question which was asked by Shrestha. What about the interference minimum condition? Interference is being given to us by the cos term. Cos term will be minimum when cos beta is equal to 0. And for what values of beta are we going to get cos 0? For twice 2n plus 1 pi by 2 values. Now, what I am going to now tell you is the clue for your question. That when I have drawn this, does it mean, since I am contributing or since I am considering the contribution of interference and diffraction together, so wherever interference is telling me that no light can be present here, diffraction is telling me light will be present here. On the other hand, where diffraction is telling me that there will be no light here, interference is giving a contribution of light there. That is why, you know, when we are actually going to see the pattern of double slit, there is no presence of complete darkness. In single slit, there can be complete darkness. However, in case of double slit or even when the number of slits increases, complete darkness condition or the screen does not show us a complete intensity is equal to 0. Because the contribution from interference gives some part of light in the position where diffraction was giving us intensity is equal to 0. So this is what happens in case of double slit. So actually, you know, if I could show you how we can draw this, we will draw the intensity something like this. See, I have not received a condition where the minima has exactly gone or touched the 0 value. All right, okay, this red is not showing very well over here. So please see, this is the envelope. This is what the intensity can be plotted. The envelope can be plotted like this. The envelope can be plotted like this, showing that in case of double slit, we are not going to get the minima value to be 0. This is not 0. This is having very little. Maybe for our plain eyes, it might be appearing as a dark thing, but in reality, it is not completely dark. All right. So this is what we are. As I was telling you in the beginning, that double slit has a contribution from diffraction as well as interference. And what we have discussed as per the interference maxima, that somewhere corresponded with the interference minima. Diffraction minima. On the other hand, wherever there was the diffraction maxima, that condition was parallel to the interference minima. And hence, something like this is observed or can be calculated. Okay. Now, if these are the 7 points that I generally tell you, path difference, phase difference, resultant amplitude, resultant intensity, conditions for central maxima, condition for secondary maxima, and condition for minima, if these are all now done for our double slit, there is one very interesting and small little point to be included in our discussion today, which actually belongs to diffraction where the number of slits is more than 1. And what is that? It is called something like missing order. The term that we are going to discuss is called missing orders. All right. And what is that? What do I mean by missing orders? It has been observed that say as per interference, where are my maximas to be found? Remember, as per my interference, a plus b sine theta, we had written I guess with m, with plus minus m pi. These are the condition. This is the equation according to which, as per which I can calculate which orders or where am I going to get the maximas. However, as per my interference or rather my diffraction, I know that a sine theta is equal to plus minus n pi is the condition for minima, which means there will be no light intensity found there. So this is as if the minima condition, whereas this is giving us the maxima condition. Now it is seen that when these two are superposed, what happens? I was expecting that the interference maxima number 3 will be visible for me. I will be seeing a bright line for the say third maxima. However, when I actually go and observe the intensity pattern, I see that the number 3 is missing or the number 6 is missing. That is why we call them as missing orders. But why is that happening? It is happening because of the superposition of a similar number of minima caused due to diffraction. In this case, please remember that the minima due to diffraction overpowers the maxima due to interference. Okay, because overall this thing is because of two diffraction slits, the condition for minima of diffraction overpowers the condition of maxima of interference. What can I show you over here? Now, suppose I have written down these two equations. Now, let us divide these two equations by each other. What I have asked you to do, that divide this equation by this equation. So, the sine theta will be cancelled, pi will be cancelled. So, what am I getting actually? A plus B by A is equal to M by N. This condition I am getting. Reminding once again that this upper equation is the condition for my intensity maxima. However, the lower one is the condition for my diffraction minima. In this scenario, say it will be easy for you all to understand if I say show you that a situation where A is equal to B, where the slit width is equal to the distance between the slits. So what will I have over here? I will have 2A, which means M by N is equal to 2 or M is equal to 2N. Correct? And remember, these are our diffraction numbers and these are diffraction orders and these are our interference orders. So what will happen when I am going to consider the value of n is equal to 1 or 2 or 3? These are all my diffraction minimas. Whereas this m over here, so in this case when n is equal to 1, m is equal to 2, this order will be absent. Or m is equal to 2, 4, 6, all these particular orders of the interference maxima will be overshadowed by the diffraction minimas on those points on the screen, and hence we are not going to see those particular expected maximas on the screen. All right, Purvita, I will tell you once again that how the orders are getting missed. I will tell you, I will surely tell you. Once again, what have we seen? We have seen that the condition for interference maxima, was A plus B sine theta is equal to plus minus m pi, where m can take up values from 1, 2, 3, 4 and so on. On the other hand, interference minimas were received for A sine theta is equal to plus minus n pi. Once again, n can take up values from 1, 2, 3, 4 and so on. Isn't it? So, these two conditions are occurring at the same place on the screen, right? For the same m is equal to 1, n is equal to 1. In this scenario, what are we going to get? The diffraction minima is going to overpower the interference maxima. All right. So if interference is giving me or telling me the result that I will be getting order number 2, order number 3, order number 4, when I'm actually going to observe it, I will see that few of those orders, expected orders, are not seen. And who has taken them away? They are actually the diffraction minima condition which has taken them away. All right. And as I was telling you, how can we do the calculation as to which orders will be missing? I had asked you to divide this equation by this equation, and from there we had received a condition that A plus B by A is equal to M by N. In this scenario, once again see, M are the orders of interference maxima, N are the orders of diffraction minima. And diffraction minima is more powerful. It has been observed. So this is like a law that we can follow. So what can we see? If from this particular scenario, I want to see or I want to find out which of my orders, which values of M will be missing on the screen. For that simplicity, what I was telling you that we have considered a situation where the slit width is equal to the slit separation. A is equal to B. So A plus A will give me twice of A. Or basically A is getting cancelled. So the ratio of M by N is 2 or M is equal to 2N. So all those M's, all those M values or all those interference maximas which correspond or which are equal to the value of 2 into N, where N is the order of diffraction minimas, these will be missing. And since N can take up values from 1, 2, 3, 4, the Or what are the values of m which are missing? M is equal to 2, 4, 6, 8. All these numbers will be missing, right? So this is the situation where I have taken the slit width is equal to the slit distance between the separation. On the other hand, we can also get some other missing orders as well, depending on what is the construction. What is that? Say, what can I do? A is equal to, or B is equal to 2A. B is equal to 2A, which means the slit width is, if slit width is A, the distance between them is twice of that. So what will I have? A plus 2A by A is equal to M by N. Or in this case, what I am going to get is M is equal to 3N. And since N is 1, 2, 3, which orders will be missing in this case? The order number 3, the order number 6, the order number 9 would be missing. So is this understood by all of you? Please let me know. Yes, very good. Purvita has now understood it nicely. So this is how. So depending on what is the construction of our experimental setup, whether what is the relation between A and B, those corresponding orders will not be seen on the interference or the intensity distribution. All right. So this was the last point which we had to discuss in terms of the double slit diffraction. Now, before we end the discussion on this topic, or before we end the topic of double slit, once again, what are the points which we must be preparing ourselves for the sake of our examination? All the 7 points that I have been telling you, the same, that those things remain for single slit as well as double slit. However, one small little term or point is extra in case of double slit, and that is the discussion of missing orders. All right. So that is actually all that you can know or deduce or calculate in terms of the double slit interference pattern. All right. So numerical problems might be coming. These kind of small little derivations might be coming in the examination. So once we are solving more and more problems in our assignments, it will be very, like the topic will be completely prepared for us for the examination. All right. So that is all for double slit diffraction, as well as that is all for today's class. So I wish you all the very best for the coming weekend. Now we'll not be having classes for the next 2 days. Sunday and Monday will be our holidays. So see you next week. Take care. Bye bye.